is from Sarah Russo from Liberty University, talking about investigation of Earth's rapid magnetic field reversals. Sarah, first.
Yes. Okay. Hello everyone, my name is Sarah Russo, and I'm going to be talking about an investigation of Earth's rapid magnetic field reversals. This is undergraduate research under the guidance of Dr. John Baumgartner. We're from Liberty University, and we're also here with the Fluid Research Group with Dr. Wayne Strasser. You will notice a slight change to the title here, but that's just because we thought that this title would more accurately reflect what we're presenting today. So what would happen if Earth had no magnetic field? We would die. So magnetic field research is super important because without Earth's magnetic field, we would be polarized by the sun. Because of the magnetic field, when we get solar storms, like when the sunspots are facing Earth, we get to see beautiful northern lights instead of getting pulverized. And so we do really need to understand how our magnetic field works, and also subsequently how reversals work, because these help us to determine future predictive models for how reversals could happen in the future. There's been a lot of talk about why reversals are happening, so because we haven't been able to really predict why they're happening and therefore have accurate modeling. So to introduce some important concepts for this, I put a picture here of the simplified Earth structure, just so everyone's on the same page, because I know people aren't geophysicists here. You can see how the crust is so much smaller in volume than everything else. The mantle is solid silicate rock, and the outer core is molten iron, and the inner core is also solid. And so let's go through some properties, specifically about the outer core. So this is an electrically conductive fluid. There's convection that's driving the magnetic field. So the outer core is where the magnetic field is being generated in, at least according to theory right now. And so this is a magnetohydrodynamic fluid, and so we have to worry about flux freeze, which is how the magnetic flux lines basically like freeze, and the convection moves the lines throughout the fluid. And so this can cause effects like bunching of the magnetic flux lines and other things like that are important when we're considering reversals. The other important note is that the Reynolds number for the outer core is very high, and so we're talking very turbulent. Making realistic simulations is very computationally intensive. We have a typical temperature range expected from 4,000 to 6,000 Kelvin, and the Rossby number is also something important to consider when we're talking about the magnetic field. Here's the equation for it. It's the ratio of inertial to Coriolis forces. So this is basically the Rossby number is expected to be fairly low, which is indicating that the Coriolis force does matter for Earth's fluid flow. So next I'm going to talk about geomagnetic field questions and theories. So we do have ohmic dissipation to worry about within the outer core. This is basically friction for magnetic fields. The geomagnetic field would drastically be fading away, assuming the Earth is very old, and so to combat this problem we have the geodynamo theories, and this is basically a way for Earth to sustain a magnetic field for long periods of time through the eddies that are like very small eddies and MHD concepts. So these computations are very difficult to do because they're trying to create and sustain a magnetic field from the eddies. This requires a lot more power than current high-performance computing can handle, just because the turbulence level is very high, and creating eddies at that small of a level is just very difficult and computationally expensive. So you can definitely see there's a problem with studying these. We do know that Earth's magnetic field has reversed many times in the past, but we don't really know how this has happened. There's thoughts that it could have been random because there hasn't really been the ability to fully test this through computational methods currently. And just from what's been tested currently, there hasn't been any correlations found so far. Especially one of the most popular models made was a geodynamo model by Glatzner and Roberts in 1995. and they were able to get one magnetic field reversal, but they had a very non-planet-like structure to their simulation, and so that just shows like how difficult it's been for scientists to be able to model these situations. And so they're basically getting stuck with trying to generate the field and unable to really study reversals in depth. They found their one reversal by accident, basically. So a possible proposed solution for this is that we could try changing the way that we're trying to study this. We could use a model that's assuming a starting magnetic field, say B naught, and then we could maybe try to bypass trying to create a field while still involving the magnetohydrodynamic equations necessary. We did find a literature paper that was saying that there could be, because of if there was an increased convection event in the outer core, then it could possibly cause a reversal, and this is because of the way that the magnetic flux lines would be bunching together at the top and potentially inducing a magnetic field in the opposite direction. So this proposed mechanism could be tested through a computational model that is involving MHD equations, and for example, the Navier-Stokes equation, including the Lorentz force here. So our candidate approach to this is to update Terra, which is a mantle convection code, to be able to change it to outer core convection. So Terra is a 3D spherical finite element code, and it utilizes a multi-grid solver method. It's for large systems with coupled partial differential equations, and it's already very well suited to spherical geometry in terms of spherical harmonics and that sort of thing. And so this code could be very easily, well, not easily, but it could be definitely changed so that we can use it for this problem as well. And so I included a sample calculation here because I will have some more calculations from our preliminary study that I'm presenting, and I just wanted to show what you're looking at. These are all going to be temperature gradient plots, and so we have some case information on the side there with the case number, and we also have a temperature gradient plot that shows like the ranges that we're looking at. And so red is going to be the higher temperatures and blue is going to be the cooler temperatures as we move forward. So our objective is to test input temperature conditions with Terra to determine if reversals will occur. So this is going to be more of a three-step process. So first of all, we're going to need to adapt Terra to outer core convection, and next we would need to add magnetic equations to Terra, and then finally test different temperature conditions on the core mantle boundary, which is basically the top layer of the outer core. Today I'm going to be focusing on our work for adapting Terra to outer core convection, and next I'll go into our methods. So we tracked our changes to Terra over two sets of calculations, and we divided this into, we categorized the changes into material properties, such as the viscosity, thermal conductivity, and compressible function of state. And then we also did the temperature changes and Coriolis force together. Specifically for the temperature changes, what we added was a spherical harmonic temperature distribution at the core mantle boundary. This allows us to input a different temperature distribution based on the order of spherical harmonics that we want.